kinetics, which is our last chapter here. So last time we started talking about a little bit about kinetics, getting into it, and a reminder that when we kind of deal with kinetics, what we're dealing with is, again, really sort of the speed of the chemical reaction, right? And remember, that's different than sort of thermodynamics, where we talked about, how whether or not a reaction would take place, if it will be spontaneous or non-spontaneous. But here we're looking really at, how fast or slow a reaction basically takes place. We started talking about the idea of rate expression, and we do that by looking at the we look at the actual sort of rate of the reaction. Everybody can hear me? Okay. Yeah.
Yeah, I can hear you.
Okay. Perfect. All right. So we started talking about the sort of rate expression, and that is based off of the balanced chemical reaction. So if we have A to the A plus B to the B goes to C to the C and so forth, we could write what is referred to as the rate expression, where we take the rate is equal to -1 over A, the change in the concentration of A over the change in time. And that would also equal -1 over B, the change in the concentration of B over the change in time. And that would equal 1 over C, the change in the concentration of C over the change in time. A couple of things we talked about. First off, we are assuming, obviously, that the reactants would be decreasing with time, which is why we do have the negatives here for our reactants. We would be expecting these guys to increase with time. And again, that's why there's no negative here. So sort of a positive reaction that's happening there, an increase that's basically taking place. The 1 over the coefficient, as we talked about last time, basically will take into account really the stoichiometry that's involved. And what that means is, instead of sort of doing a multiple relationship separately, or sort of the stoichiometry part of the calculation separately, you could kind of incorporate it into the actual calculation here. And by doing 1 over the coefficient, that will take care again of all that multiple relationship. As we talked about last time, as maybe we'll see here today as well, it is possible that you can actually just do the stoichiometry part first if you want, and then sort of do the kinetics part of it. Or again, this will sort of take it into place. We also have 1 over C. Again, that's a product, so it's positive. So remember that when we talk about sort of the change of a reactant over time, or the change of a product over time, for example, we're just talking about, say, this part of it. This part of it, which is a reactant, will end up being a negative. This part of this over here, which is basically how this particular product is changing, will be a positive number. And remember, as we talked about last time, the average rate for the reaction will be a positive number when you're there. And that's really why we have the negative there, because negative and negative there will get you a positive overall average rate. And the reason, again, we get a negative is because our reactants are decreasing with time, our final concentration will always be lower than our initial. So you get like a -2, for example. So when you do that sort of change part for your reactant, you will end up with a negative number. And again, that negative and negative will turn our average rate for the reaction into a positive number. So again, the average rate should be positive. But if you're talking specifically about how a reactant is changing over time, that probably will be negative. And also, again, if you're talking about how a product is changing over time, that should be positive to indicate that it's increasing. Any questions on the stuff we talked about last time? All right, so I think this is sort of where we left off. So why don't you take a couple moments here and see what you come up with on this particular one. We have 2.4 times 10 to the 2 grams of NOBr decomposes and a flask for 5 minutes. What is the average rate of Br2 production in molarity per second? and see what you come up with there. Remember that there's a couple different ways you could approach this, but really you want to think about maybe the two things that you're interested in the problem. So obviously we have some information about NOBR. So we can write the rate expression for NOBR, and that is that the rate would equal -1/2, which is its coefficient there. The change in the concentration of NOBR over time. We also can look at BR2, and we could come up with that the rate is equal to the change in the concentration of BR2 over the change in time. Here, coefficient for BR2 is 1, so basically it's 1/1, so you don't need to put it. It also is a product, which means it should be positive in this particular case. Any questions on that so far? At this point, we really have a lot of information, obviously, about NOBR. We have the grams. We also have the molar mass from the periodic table. We got some volume there. That's going to really allow us to figure out the molarity, right, or the concentration of NOBR. So we'll take our basically 240 grams. We will divide it by the molar mass, which if it wasn't given to you, you would get that from the periodic table. That's 109.91 grams per mole. And that's going to get you 240 divided by 109.91. We'll call it 2.184 moles. Remember, though, that that is moles and not molarity, and that is why we have the volume here. Our volume, basically 200 milliliters divided by 1,000 gets us 0.2 liters. So we can divide this now by 0.2 liters, and that will give us the molarity of how it's changing. And that's going to get us, looks like 10.92 molar. Any questions on that there? Other consideration I'm going to do up front is I could see that in the end, I'm looking for the time to be in seconds. I have my time here in minutes. So we're just going to do a quick conversion, right, to convert our minutes into seconds. That's going to give us 300 seconds. That pretty much now gives us the top part here, gives us the bottom part here. We can put it all into this first expression here, really to get the overall average rate here of this reaction. And if we do that, we would put it in, and it would be the rate is equal to -1/2 minus 10.92 molar divided by 300 seconds. So you might be asking, why did I make it a negative here? Well, it's not necessarily straight out told to you that it is negative, but the one thing that we know about this NOBR is it is a reactant, which means technically speaking, when we would have done the final minus the initial concentration, it should give us a negative number. So that's why I made it negative, because where the 10.92 comes from should come from final minus initial. And again, that should give you a negative number. And that's important here because, again, those two negatives will now turn our rate into a positive number, which is what it should be. Any questions on that? So doing that, we get a rate is equal to 10.92 divided by 300, also divided by 2, gives us a rate that is equal to, we'll call it 0.018. Looks like everybody's going with 2 sig figs on much of the stuff, so we'll go with that. And this would be molarity per second, and that would equal technically the average rate for this particular reaction. But now we're really interested, though, right, in what is the BR2 change over time. So if we look at that, that brings us to this guy. And really the number we just got here is this guy. which means that basically the rate is equal to the change in the BR2 over the change in time, which means that basically equals 0.018 molar seconds. And that would be the answer here. Question on that there. So the way I just solved this obviously was the way we sort of spoke about the other day, and doing it sort of using the rate expression. Now, a minute ago, I told you that you could do more of the stoichiometry part first and then sort of do the kinetics part. And let me just show you on this example here how that would work. And it really is kind of the same math that you're doing. But I'll just kind of pick it up and kind of show you how you could kind of do the stoichiometry part separate if you wanted to, and then sort of incorporate the kinetics part. So just going back to this number right here, the moles, this is really if we just did sort of like a regular stoichiometry problem, we just figured out there's 2.184 moles of NOBr, right? And at this point, we're interested in BR2. So if we look at the equation, just like a normal stoichiometry problem, we will see obviously that there are 2 moles of NOBr equals 1 mole of BR2. So we could really just do a regular stoichiometry problem at this point and go from NOBr to BR2, just like normal, a mole to mole relationship. And again, the moles of the NOBr would cancel, and you get 2.184 divided by 2, 1.092. BR2, my very badly written one there. At this point, we now can convert it into molarity by dividing by our 0.2, and we'll be in BR2 at this point. So if we do that, divided by 0.2, we end up with 5.46 molar BR2. We then can divide it by our seconds at this point to convert it into molarity per seconds, and you end up with 0.018 molar seconds. So again, you could do, as you see here, a basic sort of stoichiometry part separate than like the kinetics part, or you could kind of combo it together. It really is the same calculation, because if you just look at this part right here, that is basically your 1/2 that we used earlier, right? If you look right here, 1/2 is basically what the 1/2 is over there as well. So it's kind of really the same calculation. It's just sort of how you want to break it up and sort of do it. Again, you could do it as a stoichiometry problem, then a kinetics problem, or you could do 1/2 the coefficients, which basically does it for you. Any questions on that? Okay, any questions on rate expression? So we really do use the rate expression to help us figure out really, how everybody in a reaction is changing is beneficial, because we just need really one piece of information, information about either the reactant, the product, the average rate, and really from that, using really the stoichiometry relationship, we can figure out really how everybody else is changing. All right, so let's talk about some factors that actually does affect reaction rate. First off, the nature of the reactants. Basically, what sort of physical state they're in oftentimes will really affect how fast or how slow a reaction may react, or a molecule may react. If we have smaller molecules, they tend to react faster than larger ones. Gases tend to react faster than liquids, which react faster than solids. So if you just think about that, gases, right, are completely broken apart from each other. They're flying around, they're moving around, they're colliding with things. They have a lot of energy, obviously, to do that. That's going to probably increase the rate of a reaction. Liquid's still moving around a little bit, but more together, obviously. So in comparison to a gas, not going to have as much energy. And then obviously when we get to solids, things are pretty much locked into place, don't have a lot of energy, aren't really moving around a lot or anything like that. And, would be the least reactive. In terms of solids, different types of solids react or more reactive. Powder solids are more reactive than block solids, and it has really to do with a lot more surface area where reactions can sort of take place. As you might remember when we talked about maybe single replacement reactions in the previous class, there's an activity series of metals, right? Activity series of metals, basically it's like there's hydrogen kind of in the middle. There's a bunch of elements above it. There's a bunch of elements below it. And based on sort of reactivity, anybody sort of higher on the list is more reactive than anybody lower on the list. Anybody lower on the list is less reactive than anybody higher on the list. That's like when you do your single replacement reactions where you put like zinc and hydrochloric acid. Zinc is more reactive than hydrogen, which is why it replaces it, makes the hydrogen gas that you see, and the reaction does take place. Ions are definitely more reactive than molecules. So if you think about an ion is essentially, floating around in the solution, ready to go, basically, right? So they're just hanging out, floating around, they're ready to basically react, as opposed to maybe a molecule where you might need to break some bonds, you might need to break some intermolecular forces as well. So it's a little bit slower. Temperature is a big effect, obviously, on the rate of reaction. If you increase the temperature, you typically will increase the rate of reaction. It typically will obviously occur a lot faster. Vice versa as well. Obviously, if you lower the temperature, what you're essentially doing, right, with the temperature is you're essentially adding energy, right? So more energy added when you increase the temperature, more energy everybody has, the more reactive they're going to be. They're just going to be flying around a lot faster, right? And moving around a lot faster, causing more collisions to occur. And it's really sort of those collisions, right, that help a reaction take place. As opposed to if you, again, lower that temperature, you're really removing a lot of energy. Everybody kind of slows down. They're not so apt to collide very much and react and so forth. Nor are they able to, as we'll talk about when we talk about sort of the Arrhenius equation here, maybe have the correct amount of energy to sort of react and for the reaction to take place. So as we'll talk about, really there's two important things when we talk about sort of reactions and happening. And that is, one is sort of the collision idea. It has to come in contact with each other, molecules, as they're reacting. They also have to collide with each other sort of in the right location and with the right amount of energy to sort of kick off that reaction. And again, even if they hit each other, for example, and come in contact with each other, it doesn't necessarily guarantee that a reaction would occur. So sometimes, even just the act of colliding doesn't guarantee that products will be formed. Just a rule of thumb, usually if you increase the temperature about 10 degrees or so, in a lot of reactions, you will sort of double the rate of it. It will occur a lot faster. Another important sort of aspect of increasing reaction rates, or even decreasing in some cases, is the use of a catalyst. And a catalyst, again, a reminder, is it's not a reactant. It's not a product, and it does not get used up. In the reaction. So really, a catalyst is really there to just facilitate a reaction, oftentimes occurring a lot faster. As we'll see a little bit towards the end of this chapter, catalyst could be something as simple as it provides sort of a platform, if you will, for everybody to sort of come together a lot more efficiently than they would if it was not there, and they're maybe flying around trying to find each other to react. Catalysts can be, as we'll see, the same state as what's reacting. They could be different states. When we write catalysts and reactions or equations, they're typically the guys that you see up here on top of the arrow, like platinum. Maybe it says H plus, which means it's like an acid catalyst or something like that that's happening. Now, although most catalysts, and when somebody says sort of catalyst, if you will, they usually are referring to the idea of it speeding up a chemical reaction, which it definitely does, again, by providing sort of a alternative path, if you will, for everybody to come together more efficiently. There are also catalysts that, we don't usually talk too much about, but a catalyst can be something that sort of slows down a reaction, and those are sometimes referred to as negative catalysts. For example, I think we talked in nuclear chemistry, right? And the idea of like a nuclear power plant, and they have what are referred to, as, if you remember, where are referred to as control rods in there. And what those control rods do is, as we talked about, they sort of are neutron absorbers, which means with them sort of inserted into that reaction, for example, even though it's a nuclear reaction, they're essentially taking out the neutrons, thus slowing that reaction from happening if it wasn't there. So again, although I would say probably 99.9% of the time somebody says something about a catalyst, they're talking about it in terms of speeding up a chemical reaction. It definitely can be used oppositely there and be used as a way to sort of slow down a reaction, keep it in check, and stuff like that. Again, we'll talk about a couple of these things a little bit later on, homogeneous and heterogeneous, as I was just mentioning. Catalysts themselves, again, can be sort of in the same phase or different phases of what is reacting or the reactants in a particular reaction. Other really important things, obviously, is concentration. So obviously, if you sort of increase the concentration, just think about all those sort of equations and reactions we talked about this semester, right? The idea of when you increase a concentration, you basically have more moles of solute, right? Because molarity is moles of solute per liter of solution. That means that if you increase the molarity, you have a lot more moles of the solute. And if you remember, it really is like the solute that's reacting in most cases. So higher the molarity, more guys really, if you're thinking about sort of solutions floating around in the solution, ready to go, ready to react, usually would increase the reaction rate, as opposed to obviously if you had a smaller concentration, you would have sort of less people floating around in that beaker. So if you just think about sort of aqueous solutions, in a really high concentration, you have a lot of things sort of floating around. They're all over the place, they're floating, they're ready to go. You have a much lower concentration, they're more sparse kind of around floating. And that means, it's going to take longer perhaps for guys to come together as a here, where they could just turn their head or whatever, and they're basically ready to react. If you also remember when we talk about things like gases, it depends on partial pressures. So if you also think about the sort of relationship of Boyle's law, right, and pressures, as the pressure goes up, what happens to the volume? It goes down typically, right? So as we increase the pressure, typically speaking, the volume goes down. So if you think about at really high volumes, you just like crush down the volume there, which means all your gas molecules are pretty much right next door to each other, and is going to allow them to react really quickly, as opposed to if you kind of decrease the pressure, usually that implies a volume's increasing. Again, that's going to give everybody a little bit more room to kind of spread out. It's going to take maybe a little bit longer for collisions to occur. And then obviously the rate of the reaction would slow in that particular instance compared to the one where we had a much larger volume pressure. Any questions on that there? All right. So then let's talk about the rate law here and sort of what it is and how it's a little bit different from what we've been talking about. And let me first fix my arrow here. So we'll go this way. All right, so looking at this reaction, we can write a rate law. And the rate law really expresses the relationship between the reaction, the rate of the reaction, and the rate constant and its concentrations raised to a particular power. So this is definitely what is referred to a rate law, not to be confused with sort of the rate expression that we were dealing with earlier here. This is basically the rate is equal to K. This is our rate constant, as we talked about earlier. And again, that's sort of that constant relationship that we have when we look at sort of the changes in sort of concentration versus time over sort of the whole period of the reaction. Remember as well, again, these are concentrations, really molarity. X and Y, these are what are referred to as the orders. So X is the order in this case with respect to reactant A, Y is the order with respect to reactant B. And if we want the overall order of the reaction, we basically add them together. So X plus Y basically will give us, in this case, the overall order of the reaction. If there was 3 reactants, occasionally it happens, X, Y, and Z, for example, you add them together. A couple really important things here when we look at sort of the rate law versus say the rate expression. And one major thing is it is all about the reactants. Yeah, it's only the reactants. So it's really only the reactants involved in this particular reaction. And you only include reactants when you write a rate law. You may be asking sort of, what is the deal with the orders? The orders, are really sort of the proportion that's needed of those reactants to basically generate a certain rate of a particular reaction. Now, a couple important things about the orders and so forth is the orders are always found experimentally. So the orders are always found experimentally. They are not the coefficients in the balance equation. So not the coefficients in the balance equation, although they may equal the coefficients sometimes, but that is not how you find them. So not the coefficients. So what does that mean if they're sort of found experimentally? It means that typically speaking, when you have a problem, when you're trying to find sort of what the rate law is for a particular reaction, you typically will be given information. You'll be given tables, and you'll be given tables of certain things like the concentration of A, concentration of B, and you'll be given like rate information, And usually in this case, there'll be like a number of experiments, like experiment 1, experiment 2, experiment 3, 4, 5, however many experiments. So there's a couple of ways you could sort of analyze this table. And most people usually will do more of a sort of mathematical approach to it. And really look at how the concentrations are changing versus the particular rate. So for example, just making up numbers, let's just say, for example, experiment 1, the molarity there was 2 for A and 2 for B. And 2 for A in experiment 1 and 2 for A in experiment 2. And for B, it was 4 in experiment 1 and 2. And the rate here was 6, and this was like 12 molar seconds, right? We'll do that, sorry. So if we were to look at a table like this, obviously you would have information here as well. But if we were to look at a table like this, mathematically speaking, sort of the best way to do it is to kind of use an equation such as this, which is rate 2 divided by rate 1 equals k times a to the x, b to the y, divided by k times a to the x and b to the y. So first off, let me just talk about a couple of these things here. When we talk about rate 1 and rate 2, we're not necessarily meaning that you go to the table and you find entry number 1 and entry number 2. It doesn't really mean that. It just means that you need to go to the table and find 2 entries in the table. And what you're looking for when you're trying to find the 2 entries in the table is you're trying to find one entry, or actually 2 entries, where one of the entries keeps the concentration of one of the reactants constant while it varies the other. So in my example here, since there's only 1 and 2, in experiments 1 and 2, the concentration of A remains constant. Concentration of B varies. And the idea behind that is obviously we don't want more than one unknown, right? In math, it makes it really hard, obviously, if you have more than one unknown. So what we would do is, for example, we would take experiments 1's information, and usually if you pick the one that has sort of the larger rate and put it on top, you'll kind of end up with nicer whole numbers sometimes. So I'm going to put everything from experiment number 1 up on top. That means that my rate was 12 equals k times a, which was 2 to the x, times b, which was 4 to the y. And that's all the information from number 1 in the table. I'm now going to put all the information for number 2 in the table. My rate would be 6, and I would have k. Concentration of A would be 2, and concentration of B would be 2 in this case. Now I can really solve for this mathematically. If I take 12 divided by 6, that is 2. When I get to the k on top and the k on the bottom, they're both rate constants, which implies constant number. Although I don't know what the number is at this point, I do know that they're going to be the same, which means they will cancel out as well. Now, when I get to a to the x, a is 2 on top, 2 on the bottom. Again here, I do not know what the order is for x at this point, but I do know that it is going to be the same on the top guy and the bottom guy, which means that these guys essentially will be the exact same number and they will cancel out. When I take my B concentration, which is 4 on top, 2 on the bottom, that leaves me with 2 to the Y when I sort of cancel those guys out. Any questions at this point? So what that's now going to allow me to do is to solve for this. And in this particular case, you could probably easily see that Y is equal to 1. By the way, if it did not come out as pretty numbers on both sides like that, you can mathematically solve for it a couple different ways. But one way you could do is take the natural log of 2 on the left, take the natural log of 2 on the right, which will drop the Y down, and then divide those two guys to the other side. So again, if you get a number that's maybe not really easy to kind of maybe visualize what the Y would be, again, because basically take the natural log of both sides and then divide it out, and that will get you to your number. And obviously in this case, if you did that, you get 0.693 on top, 0.693 on the bottom, gives you a Y value of 1 when it's all said and done. Question on that? Now, in my made up example, what that would tell us is that the order for Y was 1. What we would do then is go back to our table. And at this point, we kept A constant and varied B. We would then perhaps, let's just say this guy was 2 and this guy was 4. We would then want to look at experiments 2 and 3, because now that would hold B constant while varying A, and we would go back in and basically do the same type of calculation. At that point, you would get the orders for X and Y. You would also be able to figure out the overall order of the reaction. And then more importantly, we can then figure out our rate constant at that point by using the numbers in the table and resolving. Any questions on that? So to kind of illustrate again, maybe, what is the effect of the orders, or how does it affect rate and stuff like that? We could just simply like look at, say, this rate law here. So let's say that we decided that, the concentration of A was 2 and the concentration of B was 2 as well. And let's just say, for example, X and Y were first order, right? So if we kind of just put the numbers into our equation, the rate would equal basically 2 times 2 in this case, which would be 4, right? Am I really bad? Really done here? Come on, there you go. And again, the reason I'm taking out this is the rate constant, so it'll be the same in every reaction we would do. So it's not really a variable, if you will. Let's say, though, that we decided to keep A the same order, but maybe B's order ended up being second order. So in this case, this is 1 and 1, X is equal to 1, Y is equal to 1. So let's just change it around, keep X is equal to 1 and Y is equal to 2 in this case. So what would happen if B was second order? How would that affect the rate? Plugging it into our sort of equation there, we would get basically 2 times 2, and then we would square it because the order on that guy would be obviously squared. That's going to give us basically 4 times 2, which is the rate of 8 in this particular case. So what happened in this particular reaction, if B had an order of 2, we see that the rate goes up by a factor of 2 as well, right? It goes from, say, a rate of 4 to a rate of 8. So it gets twice as fast. So that's really what the orders sort of play a role in. They play a role in sort of, the ratio that's needed, to kind of get that rate. And depending on, whether it's, say, first order, second order, whatever it may be, having some different orders, could either perhaps by adjusting a certain concentration, may be able to make the reaction go faster than it would if it was, say, first order or second order, right? Because if I just also double the concentration of B in that particular case, that would give us 4 squared, which is 16 times 2. We would then go to a rate of 32, right, in this case. So if I just double this guy to 4, we go from a rate of 8 in my example to basically a rate of 32, which is, again, basically a 4-fold increase. And you don't see that here. If we doubled it here, we would go up, only to a factor of 2. The rate would jump up to 8. So again, the orders, again, give sort of that proportion to how things react. And you could use that to, if you want to kind of speed up a reaction, maybe slow down a reaction, you will know which reactant you need to maybe increase or decrease to achieve that sort of rate change, either up or down. Any questions on that? Okay. So why don't you take a second here and go through this. This is, again, typical table that you would be given in a kinetics problem. We have some concentrations, we have some rates. Here's our reaction. So why don't you figure out a couple things, figure out the rate law with the orders, the value of the rate constant, and the overall order of this reaction. So why don't you give it a try and see what you come up with. So let's take a look and just kind of make sure everybody's on the same page. So like I said, this is a very typical sort of information that you're given in kinetics problems. So we could look at the equation really and sort of come up with our rate law. Again, it's going to be the rate is equal to K times our F2 to the X and our ClO2 to the Y. Again, you could write really any sort of letters you like, but we'll use X and Y. So when we have this type of table, what we want to really look for again is to have two entries where one of the concentrations remains the same and one varies. So if we look at 1 and 2 here, we can see that the concentration of F2 remains at 0.1, while the concentration of ClO2 basically varies. So I'm going to go with experiments 1 and 2 here to begin with. And again, we're going to use our rate 1, rate 2 sort of idea. So here, I like to go with my personal preferences, the one that has the higher rate to put on top, as I mentioned before, kind of gives you some whole numbers usually, rather than decimals. Nothing wrong with decimals, but you might need to do some natural logs at the end. It might not be as obvious to you sort of what the values will be at the end. So what I'm going to do is basically just put all my information for experiment 2 into that the formula we used before, which would be 0.1 to the X and 0.04 to the Y. So everything here came from experiment number 2's information. I'm now going to do the same thing here with experiment 1. So I'm going to put that rate on the bottom, which is 1.2 times 10 to the minus 3. Again, on the bottom here, our K 0.1, which is what we kept constant, and our 0.01, which we varied. First off, any questions on sort of that setup? That's again that rate 2 over rate 1 sort of guy we were looking at. At this point, we're going to do some math here. So I believe that's going to give us a 4 over here is equal to, same idea as last time. We don't know what K is at this moment, but it is a constant. So it should be the same on top and bottom. We don't know what X is right now, but again, should be the same on top and bottom, which means really these guys will also cancel out. That's going to give us our last guys here, which is going to give us 4 to the Y. And in this case, obviously, Y would equal 1. Any questions on that there? By the way, they don't always come out to 1, but in this case, we did. Now that we did one of our guys, what we want to do now is really go back, and we kept the F2 constant last time. We now want to really keep the ClO2 constant. And to achieve that, that looks like 1 and 3. We'll keep those guys constant. So we're basically going to do the same type of calculation for 1 and 3. And again, I'm going to kind of compare the rates to see which one's larger. And it looks like number 3 there is larger. So for me, again, I'm going to put all 3's information up on top. And if I do that, I get 2.4 times 10 to the minus 3 equals our K. That's going to be 0.2 to the X, and that will be 0.01 to the Y. And now come back on the bottom and put all my information for number 1 in there. So 1.2 times 10 to the minus 3 K. Here we got 0.1 to the X and 0.01 to the Y. Doing our same type of math here, we're going to divide there. That's going to give us a 2 is equal to, again, the K's cancel. When we do this guy, we get 2 to the X, and these guys completely cancel, giving us an X is equal to 1 in this case. Any questions on that so far? That now gives us the opportunity to write our completed rate law here. So we could go the rate in this case would equal K times our F2 and it is to the 1. So much like everything else in chemistry, you don't have to put the 1 up there on top. And our ClO2 also to the 1. So again, you do not have to put the 1 up on top. It's implied that it is 1. This also tells us that the overall order of this reaction is 1 plus 1, which means it is second order. Any questions up to that point there? Now that we have really completed the rate law, we've got the orders down, we now can actually use our completed rate law here and actually figure out what is the actual value of the rate constant. And we could do that by rearranging the rate law with its orders and solving for K. And that would get us in this case that the rate is divided by the concentration of F2 times ClO2. Now, your question might be, where do I get those numbers from? And the answer is, you get it from the table. Doesn't matter which entry in the table you pick. Can you choose 1? Can you choose 2? Can you choose 3? And the answer is yes, you could choose any entry you want as long as you don't mix and match and you keep very much the same values all the way across. So what I'm going to do is I'm going to actually take entry number 1 here, and I'm going to put all those guys into here basically to figure out what the value of my rate constant is. And if I do that, I get 1.2 times 10 to the minus 3 units or molar seconds divided by the concentration of F2, which is 0.1 molar. And our ClO2 for experiment number 1, 0.01 molar. 0.01 molar. Doing my good math there, 1.2 to the minus 3 divided by 0.1 divided by 0.01 gets us a 1.2. Now let's talk about units here. Got a molarity up on top and a molarity on the bottom that's going to cancel. That's going to leave us basically 1 over molar seconds, or sometimes people will write 1.2 m to the minus 1 and s to the minus 1 here. Minus 1. Any questions on any part of that calculation there? So again, these are very common things that you are trying to find in these sort of rate law sort of problems. What is the actual completed rate law with the orders? What's the overall order? And what is the value of the rate constant? And by the way, as we will learn as we go through this chapter, these units here are definitely the ones that are associated with a second order reaction. So it actually does make very much sense here. Any questions on any part of that calculation? Okay. So as we've seen here, again, a couple of things. The rates are, the orders are always sort of determined experimentally, and really the rate laws are determined experimentally. The orders or the reaction is always in terms of our reactants, not our products, so no products in there. And again, the coefficient here, this circle missed where it's supposed to circle that. And this guy is supposed to be over here. So kind of fix that there. So we see here in the balanced equation, the ClO2 has a coefficient of 2, but the actual order is first order. So we don't, like we do in sort of equilibrium, we don't take the coefficient as those exporters, as the exponents. We need to, again, experimentally determine that from the table. All right, so why don't you take a second here, the rate equation here. for NO is as follows. If the rate is 6.6 times 10 to the minus 5, when NO is 1 times 10 to the minus 6 and O3 is 3 times 10 to the minus 6, what is the rate constant? So take a couple minutes to see what you come up with. The rate law there, so we'll definitely use that to figure out what we're looking for. We got the rate is equal to K, NO, and O3. So in this case, we are looking for the rate constant. So just like we just did, they were going to rearrange the rate law here. And they were also nice enough to give us the concentrations of those guys. So we will put this in as 6.6 times 10 to the minus 5 molar seconds divided by our NO concentration, which is 1 times 10 to the minus 6 molar, and our 3 times 10 to the minus 6 molar. Going to get us looks like maybe 2.2 times 10 to the 7, 1 over molar seconds. If I didn't push a number wrong, just make sure real quick. Like it. And again, our units would be 1 over molar seconds, as one of the molarities on top and one on the bottom would cancel each other out, leaving us seconds on the bottom, molarity on the bottom, again, giving us that 1 over molar seconds. Any questions on that so far? Okay, we will stop here today for lecture